Welcome to the third stoichiometry lesson. In the first lesson, we learned about mole-to-mole stoichiometry and mass-to-mass stoichiometry. In the second lesson, we included mole particle conversions into the stoichiometry problems as well. And this is the third and final of the stoichiometry lessons where we are going to be involving mole volume conversions in addition to the other conversions that we've already spoken about. I hope you've enjoyed your snow day, but we need to do a little bit of work now. So start by doing the following question. Given the reaction 2 Mg plus O2 yields 2 MgO, what mass of MgO is produced from the reaction of 3.5 times 10 to the 22nd atoms of magnesium with an excess of oxygen gas? We're going to start our conversation about volume-mole conversions by talking about Avogadro's law. Avogadro's law states that two samples of a gas at the same temperature and pressure will occupy the same volume if they contain the same number of moles of particles. So if you look at the example on the bottom of the slide, if I have a sample of oxygen, 1 mole of oxygen that's at STP, and another mole of nitrogen that's at STP, because they are at the same conditions of temperature and pressure, they're both at standard temperature and they're both at standard pressure, they are going to occupy the same volume. And in this case, if those conditions of temperature and pressure are STP, 1 mole of a substance will occupy 22.4 liters. It doesn't matter what the substance is. As long as the substance is at STP, standard temperature and pressure, then 1 mole of that gas will occupy a volume of 22.4 liters. So Avogadro's law states that if you have two gases that have an equal number of moles and they're at the same conditions of temperature and pressure, then those two gases will have equal volumes. And the piece of information that we are going to use today is that if those conditions of temperature and pressure are standard temperature and pressure, then 1 mole will be equivalent to 22.4 liters. So the first thing we need to do is to learn how to convert between moles and volume. If you have a sample of a gas that is a 4.0 mole sample of carbon dioxide and it's at the conditions of standard temperature and pressure, what volume will that sample occupy? Well, what you need to use is the information that we learned on the last slide. Under the conditions of standard temperature and pressure, 1 mole of a gas will occupy 22.4 liters. Use dimensional analysis to convert 4.0 moles of carbon dioxide at STP to volume. As you can see in the setup here, you start with what you're given in the question, as we always do, 4 moles over 1. And then we use the conversion factor between moles and volume at STP, which is 22.4 liters for every 1 mole. What would happen here is that the moles would cancel and you end up with liters. In this case, 90 liters with a decimal point because you have 2 significant figures since your original measurement had 2 significant figures as well. What about converting from volume into moles? I have a 68.5 liter sample of oxygen gas at STP. How many moles of oxygen gas do I have? Use the same conversion factor of 22.4 liters per mole at STP to convert your 68.5 liters of oxygen gas into moles. As you can see from the setup here, you start with what you're given in the question, 68.5 liters over 1. You use the conversion factor of 22.4 liters per mole. But now we have the liters on the bottom so that the liters will cancel and will end up with units of moles. To 3 significant figures, the answer should be 3.06 moles. So let's recap all the conversions that we've discussed to date. First, we discussed how to convert between mass and moles, and the conversion factor between mass and moles was the gram formula mass of that substance. And recall that every substance has its own unique gram formula mass. We then talked about how to convert between the number of particles and the number of moles, and the conversion factor was 6.02 times 10 to the 23rd particles per mole. In this case, it doesn't matter what the particle is, because a mole by definition is 6.02 times 10 to the 23rd particles. Today we're adding in conversions for volume at STP, where the conversion factor between moles and volume at STP is 22.4 liters per mole. Take a minute to add this to your mole city. Now try these conversions. Number 1. What is the volume of 4.5 moles of hydrogen gas? Assume that this gas is at STP. Number 2. What is the mass of a 50.0 liter sample of N2? Again, assume that this sample is at STP. Number 3. How many moles are in a 75.0 liter sample of CO2, assuming that this sample is at STP? Please solve all 4 of these problems on a separate sheet of paper and use dimensional analysis. Here are the answers to the 4 problems that were on the last slide. Please check your work against my answer key. These volume to mole conversions can also be part of a stoichiometry problem. Let's go to the roadmap. When we started talking about stoichiometry, we started with mole to mole stoichiometry problems. Those were the simple ones that only required the use of a ratio. Then we added in the mass-mass problems, and in order to convert from mass of one substance to mass of another substance, you had to first convert from mass to moles, then use the mole-mole ratio to get moles of the second substance, and then convert from moles back into mass. This had to be done because, remember, each unique substance has its own gram formula mass. Then we added in the particle conversions. But we also noted that since the mole ratio is the same as the particle ratio, if you were going from particles of one substance to particles of another substance, you did not need to go convert through moles. You could just use the ratio just like you did from moles to moles. Today we're adding in volume calculations. And because the conversion factor between volume and moles is the same for every substance as long as they are at STP, if you were converting from volume of one substance to volume of another substance, you could also just use the ratios. The only conversion that requires you to go through moles would be the conversion between masses. And again, that is because every substance has its own unique gram formula mass. Please take a minute to update your Mole City roadmap to include all the parts that are on this roadmap. This is the final picture of the roadmap. You may also want to freeze the screen and print it for yourself. You will not be able to use this roadmap on the test, so please make sure that you know how to recreate this roadmap for yourself, and you can put that at the top of your test paper so that you can use it as a guide. For the next week, please make sure that you're using this both at home and in class to help you solve problems. You are going to need this for the rest of this Edpuzzle. Let's try the following problem. Given the equation 2H2 plus O2 yields 2H2O, solve the following question. Number 1. How many moles of hydrogen are necessary to make 2 moles of water? Number 2. What volume of oxygen is necessary to make 85.0 liters of water? Number 3, how many grams of hydrogen gas are necessary to produce 50.0 liters of water? And number 4, what volume of oxygen gas is needed to produce 25.0 grams of water? In each of these cases, assume that all the gases are at STP. Please use dimensional analysis to solve these 4 problems on a separate sheet of paper. Here are the answers to the 4 questions on the previous slide. Please check your work against mine. Notice in the first question that you were going from moles to moles. So all you needed to do was use the mole-to-mole ratio. In the second question, you were going from liters to liters. And so therefore, because you're going from liters to liters and the ratio of liters is the same as the ratio of the moles, you only needed to use the mole ratio in order to get the number of liters of oxygen. In the third question, you were converting from liters of H2O to grams of H2. In order to do that, you had to first convert from liters of H2O to moles of H2O, then from moles of H2O to moles of H2 using the mole ratios between H2O and H2, then convert from moles of H2 to grams of H2 by using the gram formula mass. In the fourth problem, you were converting from grams of H2O to liters of O2. To do that, you had to first convert from grams of H2O to moles of H2O by using the gram formula mass for H2O. Then from moles of H2O to moles of O2 using the mole-to-mole ratio. Then from moles of O2 to liters of O2 using the fact that a gas at STP will occupy 22.4 liters for every mole of that substance. If you did that correctly, you should have gotten 15.6 liters of O2. At this point, you should be able to convert between mass, moles, number of particles, and volume at STP of a single substance. And you should be able to convert between mass, moles, number of particles, and volume at STP of one substance in a reaction to mass, moles, number of particles, and volume at STP of a second substance in a reaction. You were given 2 sheets that had both a front and a back to be done for homework in the event that we had a snow day today. Please complete the even numbers on both of those sheets. Start with the volume-mole conversions. Then go to the volume-to-volume stoichiometry. And finally, you should look at the mixed stoichiometry sheet. Remember, just the even ones.